Hello everyone, my name is Dong Gang and I am software engineer working for SmartThings Cloud at Samsung. Today, I'm here to introduce SmartThings Context API and our SmartThings Intelligence Platform with our data analyst Dong Jong and machine learning research engineer Eric Jorgensen. First, I'm going to talk about what we want to do with the SmartThings Intelligence Platform and what kind of data is available on the platform that can bring value to our partners? After that, we will zoom in closer to the architecture of SIP. Finally, Eric and Donghyun will introduce different occupancy models that were developed to run on SIP. Millions of people use smart things to control and automate their locks, lighting, appliances, thermostat, TVs, and more to secure, monitor, and maintain their home. The SmartThings platform is the infrastructure that unifies the connected living experience in a single app and opens up a world of limitless possibilities to positively impact the way people live. We spend a lot of time thinking about the future of the home and what kind of the advanced feature we can bring to our customers and you, our partners. With you in mind, we have built SmartThings Intelligence Platform, which leverages AI and machine learning models and utilizing SmartThings data. We have done the legwork of designing how data is ingested and handled, freeing you to focus on developing your model and product. A large part of our effort has been to develop models within the SIP to sense occupancy and other contexts within the home, utilizing data generated by various home appliances. Before jumping into the detail of the SmartThings Intelligence Platform, let's take a look at some key metrics. Today, more than 130 million devices and 280 million users across the globe are connected to SmartThings Cloud. As we continue to expand support for new connectivity protocols, the number of connected devices and users keeps growing. Our key metric is the number of routines run by SmartThings users. As you may know, routines are automated sets of actions our users select to take place when a certain condition is met. Over 800 million routines per day are executed on average. Since the SmartThings platform processes all events emitted by devices on real-time basis, one of the most critical components in the cloud is real-time stream processing blocks. The SmartThings data platform is responsible for handling this. To give you a sense of each scale, our platform deals with 150,000 requests every second. Each day, that's 13 billion messages and 3 terabytes of data. Additionally, by utilizing analytic tools on our data, we have been able to define the SmartThings application and uncover the insights for potential new features. Let's talk about the architecture underlying the SIP. It's important for us to make a routine straightforward and easy for users and to build effective routines. We need good triggers. Let's take an example. After you leave your home, if you want to turn off the lights or TV automatically, you would need a specific condition that signal you have left. Typically, this would involve setting up switches or door sensors. However, we believe that with the amount of data we collect, we can infer such activities without additional devices. The SIP is designed to execute machine learning model based on event data from devices and infer the context of what's going on in the home. It's designed to work in conjunction with existing SmartThings cloud servers. Let's dive into three key features. First, the SIP delivers input data instantly for real-time inference. If there is a silent delay, it can negatively affect the user experience. Therefore, we have integrated with our data platform to ensure our models receive necessary information, such as device events, time zone data, or other information. Some models require past inference results to make an accurate prediction. So we also store historical inference results and provide them when needed. The second key feature is inference model pool. In simple terms, each user has flexibility to pick and choose models based on their needs. As you can see, various inference models like A, B, and C are listed in our model pool. Model A can be set to operate at my home, while Model B at my office location. This functionality is managed by our microservice named CNET. Third and most important, context derived from this inference result is provided through the SmartThings Context API, so that can be used not by only SmartThings, but by you and our partners to deliver users better experience. Users and partners can receive inference results in real time through smart app or event subscription. However, this inference result is subject to user agreement. Additionally, for our user, these inferred results can be integrated into their routines. Imagine a user who only has Samsung appliances without extra sensor. If the user enables the occupancy model, they can use the inferred result as a condition. For example, when you leave for work in the morning, it can automatically turn off the devices or activate the security mode. Next, I'd like to introduce Eric, who is a part of a team of SmartThings researchers behind the development of our occupancy inference model.
Thank you, Dongwon. Hi, my name is Eric Jorgensen, Senior Machine Learning Research Engineer with the SmartThings Intelligence Platform. I'll be exploring how we developed an exciting new feature called Derived Presence Detection, on which developers can design new features and routines through the SmartThings Context API. Rather than having to worry about the privacy concerns of installing cameras throughout your entire home, our presence detection model enables the wide variety of devices you already own to be used to also detect user presence. This will unlock an exciting new level of routines and automations for our users. With the thousands of different types of devices that can already be connected through SmartThings, most of those devices output events that can be used to indicate a user's presence. The device events can be categorized into two main classes: manual and presence-correlated devices, interaction events. We define manual interaction events as those which can only be triggered when a user is physically present at their location. You can imagine manual events like opening the fridge door or starting your stick vacuum cleaner, and they tell us that someone must be present at the location. Presence-correlated events, on the other hand, must be likely to occur when a user is present, but could also be triggered remotely or by other means. Events like motion detection can hint towards possible presence, but also could be triggered by your pet or some motion outside the home. To reliably model our presence at a location, we rely on a combination of 3 signals: mobile presence, manual interaction, and security arm state. Manual interaction, as I just mentioned, are the device events that only occur when a user is physically present and interacts with their devices. If the user enables mobile presence on their smartphone or tablet, they have the ability to trigger automations when they arrive to or leave from their home. Mobile presence events say that the user is present or not present each time they enter or leave, which, with those state change events, allows us to create a timeline of user presence throughout the entire day. Finally, users with SmartThings Home Monitor can set their security arm state. When a user disables their system, and they are most likely at home or sleeping. Otherwise, if they arm their security system, we know that it's likely that no one is present. From those security system changes, we can construct a timeline similar to how we do for mobile presence. With any of those 3 presence signals, we can derive a ground truth presence signal that is used for training our model. As seen in this example timeline, any one of those can tell us presence, but the combination of all 3 can give us a more robust label for presence throughout day and night. Now, in the absence of those ground truth presence signals, we design a machine learning model to take other signals to determine whether a user is present. We use a combination of recent device activity, historical activity, and current context as inputs to our machine learning model. Recent device activity measures how many manual and presence-correlated events are occurring now and in the recent past, say the last 90 minutes or so. If the user's devices are firing off more events, they're probably home. If there's no activity at all, there's probably no one home or just everyone's asleep. Historical activity measures the usage patterns of a user's location, other similar locations, and the general patterns of usage in their region or country. If you live in California, we want the model to predict your location presence differently than if you live in New York. Finally, context takes into account other cues like the day of the week or whether it's a holiday. Users will have much different activity on a workday than a weekend. We combine all these signals, feeding them into our machine learning model to predict whether someone is present at a location at that instant. We then train the powerful XGBoost model, which is a robust and open source machine learning architecture. This model is designed to improve prediction accuracy by aggregating together multiple predictions on simple combinations of our input presence indicator signals. For example, say it's 11 a.m. and there's no device activity at your location, you're probably away at work. Or perhaps the lights just turned off and the air conditioning temperature was set just a bit cooler. You're probably home and heading to bed. With tens or even thousands of combinations of these types of signals, XGBoost is predicting whether a user is present at a location. Using XGBoost allows us to handle this wide variety of input signals with fast inference times so that users can experience very minimal latency. Unlike black box neural network models that can be impossible to interpret, XGBoost is lightweight and allows us to directly follow those input signal combinations that lead to the model's prediction. Finally, to ensure a robust model, we train with device interaction events from locations in the US and Korea to predict when users are present. Now, this presence detection model was designed to accommodate users with a wide variety of devices, and we find that derived presence detection will work best when users have more devices, especially those appliances that can give us more concrete signals of user presence that come with the manual interaction events I was talking about before. At the same time, this model is going to struggle when users aren't interacting with their devices. As you might expect, when you're home and sleeping, your device activity looks exactly like when you're asleep or when you're away. As we continue to unlock the power of presence detection for SmartThings users, we're focusing on 3 main areas. We're working to improve presence labeling with other signals like sound detectors or power consumption or even door lock events, among others. We're tuning our models to automatically measure how well device types can signal a user's presence. You might imagine that lights turning on would tell a different story than when you activate your Jet robot vacuum cleaner. And finally, we're incorporating user testing and feedback to ensure that this feature works for the variety of ways our users live in and design their smart homes. Now, these are the models our team has been working on, but I'm excited to introduce you to Dongyoung Jung from Samsung Research, who has been working on some new models that add quite a lot of nuance and richness to the way SmartThings is detecting occupancy and context.
Yeah, thank you, Eric. Hello, everyone. I'm Donghyun. We've been doing a lot of exploring and innovating around how we can make occupancy sensing better and easier for the user. Part of what makes SmartThings so powerful is that we are a hardware and software platform. We can leverage our Samsung SmartThings appliances as well as our rich ecosystem of partner devices to come up with some pretty innovative ways of determining occupancy. I'm excited to tell you about it. Similar to the models Eric been working on, we propose a lifestyle-based hidden marker model that use device manual events. The clustering part determines the user's personal time zone and considers the user's lifestyle. Then, the hidden marker model infers whether someone is present or not. There are 3 issues addressed when developing this model. The first is identifying as many manual interaction events as possible. As previously mentioned, the basis for occupancy primarily revolves around manual events. For instance, if you operate the laundry at 9 p.m., it suggests that you are at home. Similarly, if you consistently leave for work or school on weekdays and there is no device activity, it's a strong indicator that you are at home. However, if a TV isn't connected to SmartThings and someone uses it at 9 a.m., we can deduce that someone is home. In essence, our team focuses on identifying more manual events, while your responsibility is to link additional devices to SmartThings. The more devices you connect, the more precise our occupancy inference will be. Next, we delve into how we integrate user lifestyles into our models. One consideration is the variation in time to take leave device after each use, depending on the time of day. In such a scenario, for instance, some might use particular devices before heading to work. In such a scenario, we would import their presence for only a shorter while, and then reduce their absence. Conversely, in the evening when we return home, we often use several devices before retiring for night. Let's say the last activity was operating washer before going to bed. Even if there is no subsequent device activity, it's more probable that users remained at home. This forms the basis for our inference of extended occupancy during nighttime hours. In essence, the duration import for occupancy shifts based on when the device was last activated. Another way we increase the amount of data informing our model is by categorizing users by what we call personalized activity cluster. We sort users into 24 clusters, which is essentially patterns of activity. We use a variety of data to identify which clusters to sort them into, regardless of where in an actual day or time zone their workday is. Once sorted into their cluster, we can better train our models to infer occupancy within each cluster. Third, we utilize sensing data. Environmental information can be collected by home appliances such as air conditioner and air purifier, and includes the temperature, humidity, fine dust, and power consumption. Let's dive deeper into fine dust and power consumption. Through our data analysis, we observed a sharp increase in both concentration of fine dust and power consumption when people are active within their homes. These metrics soar often several-fold compared to when the home is vacant. Based on these findings, we crafted a model designed to detect such spikes associated with occupancy. We termed it the fine dust change-based model. Moving forward, we are committed to enhancing the accuracy of occupancy detection through three primary strategies. First, integration of additional devices manual manipulation data. Second, incorporation of sensing data specifically related to occupancy. Third, emphasizing personalization. Recognizing that every household exhibits unique lifestyles, we aim to tailor our approach to cater to these differences. By implementing these measures, we are confident in continually improving the efficacy of our occupancy inference model. Next, I'd like to invite Eric back for a moment.
Hello, everyone. So you just heard about these two models. When registering a model in Synapse, it is set to define inference conditions. Thus, if there are two occupancy models, the model that performs better for your location will be selected based on previously set conditions. At present, we're catering to a select group of users. However, the SmartThings Intelligence Platform, along with the models we've highlighted today, are fully functional in our production environment. As we look forward to the future, our primary goal is to hone and broaden our models to encompass more detailed elements of the home context. We hope that this has been a valuable introduction to the SmartThings Context API, our SmartThings Intelligence Platform, and the hard work and research that has gone into developing it. We don't have much time left, therefore we will be happy to take your questions in the networking zone, and please enjoy the rest of SDC.